Okay, hello Trian. This is your assignment for Dynamics Basic 3. Okay, unfortunately, I'm not going to be able to return this worksheet on time to you because I got COVID and yeah, your worksheets are basically stuck in school and I'm stuck at home. Alright, so I'm just going to show a video to tell you the main key ideas about how to do a question like that. Right, so when you drop a steel ball bearing into oil and water, alright, what is the initial acceleration of each ball bearing? Right, we need to be aware that when we talk about initial acceleration of the ball bearing drop from rest, right, the initial state is at rest, right? So actually, since it's at rest, there's no air resistance, water resistance, or oil resistance, right? The three things follow the same concept. They oppose motion, right? So if there's no motion, the force itself doesn't exist. Okay, so if I were to draw a free body diagram of this ball bearing by itself, the only force is weight, and that is my net force. I substitute net force equal mg, ma, and that will give me mg equal ma, which means my a is 10. Right, so that's the acceleration of each ball bearing. Whereas in water or oil, it doesn't matter because initially there's no air resistance, oil resistance, or water resistance. Right. State the forces acting on each ball bearing. Okay, this one I apologize, the question is a bit vague. Right, actually they're trying to ask what are the forces on each ball bearing as they pass through the water and oil. Right, that means once they start moving, what are the forces? And the forces should be weight, right, which we've already talked about, and drag force or resistive force. Right, and that is when it starts moving. Alright, so these two should have been separated questions. Okay, so I apologize for that, the question isn't very clear. Okay, I think this statement here, do not write liquid resistance or water resistance, is a bit old. Alright, you don't have to worry about it. We'll actually accept water resistance. Okay, so yeah, please ignore this red sentence. Right, water resistance perfectly fine. Liquid resistance I would like less because it's already stated here is water, so I prefer you write water resistance or oil resistance. Right, but drag force and resistive force are acceptable alternatives. Right, so this is the motion of the water as, or rather as the ball as it falls through the water before it hits the bottom. Alright, so you can see something like that. Okay, explain the movement of the ball between 0 and 2 seconds in terms of the forces acting on it. Right, so you can see that from 0 to 2 seconds, the velocity is actually increasing at a decreasing rate, and it will reach constant velocity after 2 seconds. Right, so why is that so? That's because that at the initial start, we know that there's only weight, right? So that at t equals 0, there's only weight, so the acceleration is 10, right? But as time progresses, the ball starts moving, right? When the ball starts moving, it gains water resistance or drag force or resistive force. You can use any one of these three terms, right? And that as a result of this force increasing, the resultant force drops. Alright, again, you should draw a free body diagram here to assist you in describing the question. Remember, the qualitative question requires you to either still draw diagrams or write out equations to help you answer it. Right, so now you know that the weight is the same and the drag force is increasing. Right, you should realize the resultant force is actually dropping. Right, and if the resultant force is dropping, you know this directly is proportional to acceleration, and acceleration is the gradient of the graph, right? So you should expect the gradient of the graph is dropping, just as what this graph is showing, right? So the standard answer is something to the degree of, yeah, as the ball bearing is dropped from rest, it only has weight, right? Therefore it accelerates, right? As the speed increases, the drag force increases, right? Hence the resultant force on the ball increases, and this increases, as the speed increases, the drag force also increases, hence the resultant force decreases, right? Because if you had drawn a free body diagram, you will know why the resultant force drops, because weight is the same, drag force is increasing, right? So the downward force is minus the upward force is getting smaller, right? And this decreases the acceleration, right? And eventually the drag force equals to the weight, right, which is somewhere here, right? You can see this almost horizontal part, right? So when the drag force equals the weight in magnitude, right, there's no resultant force and no acceleration, so acceleration is 0 and the ball reaches its steady speed, right? Right, oil is more viscous than water. How to show the motion of the ball bearing when dropped in oil? Right, more viscous means that there are more molecules per unit volume, right? So it's like if I walk in air versus I walk in water, which one got more resistance? If all else are equal, clearly water, because there's more molecules I have to push aside to move, right? So if oil is more viscous, oil is like the more molecules version of water is to air lah, right? So clearly this one will hit its maximum speed earlier, and the maximum speed will therefore be lower, right? So the graph will look something like that. Alright, so firstly I will have roughly the same shape, but I will hit my maximum speed earlier, right? So you can see I hit my maximum speed earlier. When exactly doesn't matter lah, as long as you show me hit earlier, plus the maximum speed is lower. Okay, so these are the 2 points we look out for. Right, so if we look at a shuttle launching off from Earth, alright, generally what they do is that they try and fire, they burn gas that is emitted downwards, right? So when they push the gas downwards, there's an outward force on this space shuttle, right? So the three main thrusters, three main engines have a 1.7 millinewton thrust each, plus 2 rockets each producing 23 meganewtons of thrust, right? So these meganewtons, right? So total thrust is achieved after 0.5 seconds, right? So we look at the total thrust is 23 plus 3 times 23 times 2 plus 1.7 times 3, right? Yeah, so draw the forces thrust, right? Thrust has to be outwards lah, right? Because since I need to launch the rocket outwards, there must be some outward force to push it up that is greater than weight, otherwise the rocket cannot leave the ground, right? Right, calculate the acceleration 0.5 meter after ignition, right? So if you 0.5 second after ignition, all the thrusters are on, so you 3 times this plus 2 times this, right? Then you minus the weight, which can you find? Yeah, you can find because of this, right? And you got MA, right? So it's not that difficult, right? So you should get acceleration is 16 meter per second square, right? So acceleration is 18.8 meter per second square at 1.1 second, right? Explain why the value of acceleration in B, right, is less than acceleration at 1 second, right? So acceleration at B is at 0.5 seconds, right? So later on, how come its acceleration get heavier, right? This one is something that you never learned before, so I'll just go through with you. In general, rockets, fuel is a very large part of their weight, right? So as the rocket burns the fuel, right, and it actually the whatever is produced after the fuel is burned, right, is actually discharged through this part, and that's what exactly gives the thrust force outwards, right? Because this fuel is being pushed out here, right, which is the Newton's third law action pair, right? That produces the thrust outwards, which is the reaction pair, right? So suffice to say that the fuel is being discharged through the rocket, right? The rocket's mass actually decreases substantially, right? So as the mass of the rocket decreases, right, for the same forward force, right, I get a smaller weight for one thing, so clearly my net force increases, and also my mass drops, and both of these things can conspire together to give me larger acceleration. Right, okay, so with that, yeah, good luck for your while. Alright,